$10,000 down to a mere 18 bucks. That is the jaw-dropping reality of a brand new AI training breakthrough we are looking at today. I mean, imagine literally slashing your reinforcement learning costs by over 99%, all while actually improving the performance of your AI agents.
Welcome back to the Hidden Layer Decoding Artificial Intelligence. In today's explainer, we're breaking down a brand new paper from Tencent Youtu Lab that completely flips the script on how we optimize large language models. The value here is absolutely massive. We are going to explore exactly how you, as an applied engineer, can get specialized, fine-tuned agent performance without updating a single model parameter. You're getting the heavy-hitting benefits of reinforcement learning, but at a total fraction of the cost.
Now, you might be wondering, if we aren't updating the weights, how in the world can a completely frozen AI learn from its own mistakes? It sounds impossible, right? Well, I'm going to share a secret technique a little later in this explainer that allows frozen large language models to introspect and adapt with practically zero training data. Stick around, because understanding this is a real game changer for how you build agents.
All right, let's jump right into Section 1. The fine-tuning dilemma. Why parameter updates are holding agents back.
So, we know large models are fantastic generalists, but out of the box, when you deploy them into highly specialized real-world domains like complex math or deep web searching, they tend to stumble. Applying traditional reinforcement learning to fix this is honestly a nightmare for applied engineers. And there are 4 massive reasons why. First, computational cost. It will literally melt your GPU budget. Second, poor generalization. The moment you tune a model to be a math genius, it suddenly forgets how to browse the web. Third, data scarcity. You need massive, high-quality annotated datasets, which takes forever. And finally, diminishing returns. Engineers are forced into this terrible compromise where they have to tune smaller 32 billion parameter models instead of leveraging the massive state-of-the-art ones. It's a classic cost-performance trap. That brings us to the solution in Section 2. Enter training-free GRPO. Context space over parameter space. The researchers over at Tencent Youtu Lab asked a pretty brilliant question. Do we actually need to update parameters to apply reinforcement learning? Their answer is a resounding no. Notice how vanilla GRPO uses numerical advantages and gradient ascent to fundamentally rewrite the model's brain, its parameters. But with training-free GRPO, the model stays completely frozen. Instead of a numerical advantage driving those expensive weight updates, it uses the LLM itself to generate a semantic advantage, which then updates an external library of experiential knowledge. The model itself doesn't change, its context does. Okay, Section 3, the secret semantic advantage, extracting high-quality experiential knowledge. So here is that secret technique in action. Following principles that align perfectly with the AGNE framework for agentic workflows, the system prompts the frozen LLM to look at its own past rollouts and literally articulate why certain outputs succeeded and others failed. It's guided self-reflection. A controller then manages this semantic experience using 4 specific inference-only operations across optimization steps. It can add a brand new rule, delete a past experience that proved to be low quality, modify and refine an existing rule, or simply keep the library entirely unchanged. It is continuously curating its very own rulebook. Seeing this applied to verifiable AI agents is just gold. Take this geometry problem from the AIME benchmarks. In one trajectory, the agent finds an intersection point, but it's physically outside the bounds of the triangle segment. The system spots the failure, compares it to a successful trajectory, and extracts a hard logical rule. It realizes that just crunching the numbers isn't enough. It actually has to verify the physical geometry. The absolute crucial point here is this exact quote generated by the model itself. Always validate that mathematical solutions satisfy geometric constraints. The frozen model has literally codified its own failure into a reusable logical rule. In future interactions, this rule is injected right into the context prompt as a token prior. It's essentially giving the model a memory of its past mistakes before it even begins to answer. The model hasn't been retrained at all, but it acts smarter because it's carrying that experiential knowledge. Moving right along to Section 4, Real-World Applications, Math Reasoning and Web Searching. But does shifting to context space actually hold up in rigorous out-of-domain applications? Well, we tested this on complex math and web searching using the massive DeepSeek v3.1 Terminus model. After just 3 learning steps on only 100 sample problems, performance on the AIME benchmark leaped significantly.
And here is where the AI-GNE framework's focus on efficient tool use really shines. As the model learned, the average number of tool calls actually decreased. The learned experiential knowledge helped the agent discover shortcuts and completely avoid erroneous or redundant tool calls. So it didn't just get smarter, it got significantly more efficient. And this is exactly where training-free GRPO destroys traditional fine-tuning. If you take a model fine-tuned specifically for math, like Retool, it scores great on math, but drops to an abysmal 18.3% when you pivot it to a web searching task. It becomes entirely domain-locked. But with training-free GRPO, because the base model remains completely frozen, it preserves all of its massive generalizability. You just swap out the experience library and the context prompt, and you can instantly switch from state-of-the-art math reasoning straight over to state-of-the-art web searching. Which brings us to Section 5, the Applied Engineer's Advantage, real implementation and massive cost savings. For the applied engineers watching this completely redefines the workflow and the economics of deploying specialized AI agents. You are no longer chained to the burdens of maintaining multiple fine-tuned models. Just look at the staggering financial contrast here. Training a 32 billion parameter model using vanilla reinforcement learning takes about 20,000 GPU hours. That will run you roughly $10,000. In contrast, running training-free GRPO on a massive 671 billion parameter API model takes just 6 hours and costs exactly $18. You are getting vastly superior performance on a much larger model for literally pennies on the dollar. And here's the kicker: 0 dedicated GPU clusters required. Think about it. When you fine-tune a model, you have to host it. If you have a specialized, low-traffic use case, paying to keep a dedicated GPU cluster running 24/7 is an economic sinkhole that will absolutely make your CFO cry. By optimizing in the context space instead, you can leverage shared, pay-as-you-go API infrastructure. You only pay for the tokens you actually use. It's a total paradigm shift.
This shift from parameter space to context space is a monumental game changer for building agile, highly capable, and extremely cost-effective verifiable AI agents. So, I'm going to leave you with this provocative question. As models get larger and context windows expand, will context space optimization replace fine-tuning entirely for agentic workflows? We would love to hear your thoughts, so let us know in the comments below. Make sure to subscribe to The Hidden Layer for more deep dives, and we'll see you in the next explainer.